Alright, let's talk about the product and quotient rules, 2.4. So, the product rule tells us that the product of two differentiable functions is differentiable, and it also gives us the way to differentiate that product, right? So if f and g are both differentiable, then so is f times g, and the derivative of f of x times g of x is f of x times the derivative of g of x plus g of x times the derivative of f of x. So it's a little bit more complicated. You can't just distribute the derivative to f and g. In other words, the derivative of f times g is not the derivative of f times the derivative of g. It would be nice if that were true, but it's not. Okay. However, the derivative of f times g is f times the derivative of g plus g times the derivative of f. Okay. Here's a proof of the fact. So derivative of f times g by definition would be limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x all divided by h. Okay. Now, if we do a little bit of a fancy manipulation by adding and subtracting this particular quantity, then that allows us to, on the next step, factor out an f of x plus h from this first group, and then we're left with g of x plus h minus g of x. And from the second group, we can factor out a g of x, and that'll leave us with an f of x plus h minus an f of x. And then what we can do is we can distribute the limit to f of x plus h. We can distribute the limit to g of x plus h divided by, g of x plus h minus g of x divided by h. Okay. Here, we can just pull the g of x out because it doesn't depend on h at all. So we can just call this g of x, and then we can distribute the limit to f of x plus h minus f of x over h. Okay. And then that should look really familiar, right? This thing is just g prime, this thing is just f prime, so what we have, and the limit as h approaches 0 of f of x plus h is just f of x, okay? So what we have is f times g prime plus g times f prime, okay? And that concludes the proof. So, so I want to give you a couple examples of this, and maybe this proof will make more sense to you after we look at a couple examples, after you understand the statement a little bit better. So you might look at these examples, and then if you didn't understand the proof, you could go back and watch that portion of the video again. Not that I'm going to ask you to prove it on a test or anything like that, but anyway, let's practice. So let's calculate dy dx if y equals 4x squared minus 1 times 7x cubed plus x. Okay, now you don't actually even need the product rule for this because you could just multiply these out. So I'm going to give you two ways to do this. So here's the first way. So here's our first solution, is that we could just FOIL this, right? We could do 28x to the 5th plus, it looks like we've got a 4x cubed minus a 7x cubed, and then minus an x. So y is 28x to the 5th minus 3x cubed minus x. Right? So that's just y, but now finding dy dx is easy. We don't even need to use the product rule. We can just use the power rule for each of these terms, right? So we would do 5 times 20. Oh, what is 5 times 28? 140, I think. Oh, let me double check. 28 times 5. 140. Yep. So this would be 140 times x to the 4th. Minus 3 times 3 is 9, so 9x squared minus 1, right? And that's one way to find dy dx. But now let's verify that that's correct by using the product rule. So solution 2 is to use the product rule here. So for the product rule, I'm thinking of this function as f, and I'm thinking of this function as g. Okay? And I want to do f times g prime plus g times f prime. Okay, so this is going to be f times g prime plus g times f prime. So that's going to be 4x squared minus 1, there's f, times g prime. So g prime would be 21x squared plus 1, right? So there's f times g prime. Then I'm going to add g times f prime. So g is just 7x cubed plus x. F prime would be 8x minus 0, so really just 8x. Right, so there's g and f prime. Right, so I've got f times g prime plus g times f prime. The rest is just a matter of simplification. So we can FOIL these now. 4 times 21, oh goodness, 84. So 84x to the 4th. And then plus a 4x squared minus a 21x squared. So 4 minus 21 is negative 17. Oh goodness, man. You're going to have to check my arithmetic. And then minus 1. Okay, and then over here we're going to have a 56x to the 4th. And then an 8x squared. And if we combine our like terms now, 84 plus 56, well, the 6 plus 4 will bring this to a 90, and then 90 plus 50 would be 140. Negative 17 plus 8 is negative 9. And then minus 1. So sure enough, right, we got the same answer as what we got before when we used the product rule. Okay, so there's one example. Let me give you another one. I'm just going to use the product rule for this next one. I'm not going to multiply everything out because actually, as you'll see, it would be quite a pain in the butt to do that. So let's work out this one. We've got y equals x squared plus square root of x times 1 over x minus 3 over x to the 4th plus x to the negative 2/3, okay, times 2x cubed plus 3. Okay, so let's say that this is our beast of a function that we want to differentiate. So this time we actually have 3 functions. Well, we could kind of think of them like 3 functions, f, g, and h, but we don't have a product rule when you're dealing with 3 functions at a time. So I think what I'm going to do, well, first of all, let me rewrite all of these in terms of exponents. Square root of x is the same thing as x to the 1/2 power. 1 over x is the same as x to the negative 1. 3 over x to the negative 4, or 3 over x to the 4th would be 3x to the negative 4. Okay, so we've got this scenario. Now I think what I'm going to do is I'm going to treat these first 2 factors as just a single function. So I'm thinking of this as f, and then this last one I'll think of like g. You don't have to group them that way. You could do the first one as f and then the last 2 as g, or you could even rearrange the terms or rearrange the factors if you wanted to, and then group them differently. It really doesn't matter, but I'm thinking of this as f and g. And now dy dx is going to be f g prime plus g f prime. Right? That's what the product rule says. So it's going to be f times g prime. G prime, let's see, that would be 3 times 2 is 6, so 6x squared So there's f times g prime. Okay, so this is f, and this one is g prime. Okay, plus g times f prime. And now f prime is going to take a little bit of work because f prime itself is going to require a product rule. Okay, so f prime itself, maybe, so if I break this down further, maybe I can call this h1 and h2. Okay, and I want to do h1 times h2 prime plus h2 times h1 prime. Okay, so let's see if we can do this. So it's going to be h1 times h2 prime. So that's x squared plus x to the 1/2 times h2 prime. So that's going to be negative x to the negative 2. Negative 4 times negative 3 is positive 12, so plus 12 times x to the negative 4 minus 1 is negative 5. And then minus 2/3 times x to the negative 2/3 minus 1 would be negative 5/3. Okay, so there's h1 times h2 prime. But now we need to do h2, so we need to do plus h2 times h1 prime. So h1 prime is going to be 2x plus 1/2 x, right? 1 times 1/2 is 1/2, and then 1/2 minus 1 is negative 1/2. So it's going to be 1/2 x to the negative 1/2. Okay, so trying to squeeze all that in there, but anyway, so this whole thing is f times g prime, and then this is g, and the stuff in the square brackets here is f prime. Okay, now the rest is just algebra. Just algebra, I say. I'm not sure how crazy I'm going to get with the simplifying here. I mean, it would probably be nice to absorb the 6x squared into this first group. We would get a 6x to the 4th plus a 6x to the 2 plus 1/2, so 4/2 plus 1 is 5/2, so plus 6x to the 5/2 times, I might change this back to like 1 over x minus 3 over x to the 4th plus 1 over x to the 2/3, I suppose. Anyway, so that's that first group. Second group, oh goodness, we can call this 2x cubed plus 3. I mean, we could distribute this. We could distribute it. It's not going to be pretty. Well, let's do it. Let's see what we get. So x squared times x to the negative 2 would just be 1. So we have a positive 1 times a negative 1, so that's going to be negative 1. And then x squared times 12x to the negative 5, that's going to be 12x to the negative 3. And then x squared times negative 2/3 x to the negative 5/3. That's going to be negative 2/3 x to the 1/3, right? 2 is 6/3. 6/3 minus 5/3 is 1/3. So this is going to be minus 2/3 x to the positive 1/3. Okay, now distributing the x to the 1/2. X to the 1/2 times negative x to the negative 2. Negative 2 plus 1/2. Negative 2 is negative 4/2, right? So plus 1/2 would be negative 3/2. So we'll have minus x to the negative 3/2 Oh, this is so nasty. X to the 1/2 times 12x to the negative 5. Negative 5 is negative 10 halves. Negative 10 halves plus 1/2 is negative 9 halves. So this would be plus 12x to the negative 9 halves. And then x to the 1/2 times negative 2/3, x to the negative 5/3 is going to be minus, I've run out of room, minus 2/3 x to the 1/2 minus 5/3. Common denominators there would be 6, so I can call this 3/6, and I can call this negative 10/6. So 3/6 minus 10/6 is negative 7/6. Okay, that's just the first group. Then you have to do the second group. Oh, I give up. I'm not going to finish the rest. It's just algebra. It's just nasty algebra. But there's no calculus there. There's no calculus involved with that. Anyway, the main moral of the story was this, right? Understanding that when you do have three groups, or three factors, right? You can group the factors however you want, but you need to treat like one of the factors as f, and then, or one group of factors as f, and then the other group of factors as g. But then you still apply the same product rule, right? F g prime plus g f prime. Sorry, that may have been confusing to you. Okay, so that's the product rule. I made this problem up, by the way. I don't think you'd be given anything quite this nasty in the homework. I definitely wouldn't give you something this nasty on a test or a quiz. but that's that one. Okay, so that's the product rule. Let's talk about the quotient rule. So the quotient rule says if f and g are differentiable at x, and if g of x does not equal 0, then f over g is also differentiable at x. And, moreover, we can give the formula for it. So the derivative of f of x divided by g of x is going to be g of x times the derivative of f of x minus f of x times the derivative of g of x divided by g of x squared. Okay. So again, we can go through the proof of this, right? So by definition, the derivative is going to be the limit as h approaches 0 of f of x plus h over g of x plus h minus f of x over g of x, all divided by h. Now we can get common denominators and then combine those two expressions. What we would end up with is f of x plus h times g of x minus g of x plus h times f of x all over g of x plus h times g of x all over h. Well, this denominator, g of x plus h times g of x, we can just bump down and put it with the h down here. So this is what we get when we combine those two expressions. Now, just like in the previous proof, we're going to do something a little bit clever. We're going to add and subtract an f of x times a g of x, so that we haven't changed this, right? We're just adding 0, right? We're adding 0. But the reason that we want to do this is that now we can factor out a g of x from this first group, and we can factor out an f of x from the second group, and let's see what that looks like when we do it. So when we get that g of x out of there, what we're left with is f of x plus h minus f of x. When we factor out the f of x, we're left with a g of x plus h minus g of x. And if you squint at that just hard enough, you can kind of see the makings of an f prime right here, and you can kind of see the makings of a g prime right there. So in fact, we can get there by splitting these, splitting this difference, okay, and putting the h with the f of x plus h minus f of x, and with the g of x plus h minus g of x. We can also, while we're at it, take this g of x out because it doesn't rely on h, or it doesn't depend on h at all. We can move the limit there. We can also take the f of x out, distribute the limit there. And then down in the denominator, the h that was there has now been absorbed up here in these difference quotients. The g of x can be taken out because it doesn't depend on h, and the limit can be distributed to the other g of x plus h. Okay, so now if we take these limits, this just by definition is f prime, this just by definition is g prime, and the limit as h approaches 0 of g of x plus h is just g of x. So in the denominator we have g of x times g of x, or in other words g of x squared. So that's the proof of that fact. Again, I want to give you a couple examples, and then after I give you some examples, it might be a little bit more clear what the meaning of all of this is. And so it might make more sense to come back and look at the proof again if you're interested. But let's look at some examples for now. So again, let's practice differentiating. So we're going to find dy dx. Let's find dy dx if y equals x cubed plus 2x squared minus 1 divided by x plus 5. Okay, so I'm thinking of this numerator as f, and I'm thinking of this denominator as g, and to differentiate a quotient like that, we're going to do the bottom times the derivative of the top minus the top times the derivative of the bottom, and then we're going to divide by the bottom squared. So there's a little, I guess you would call it a mnemonic device that I learned to help me remember this rule, and it goes low d high minus high d low over low squared. So it's low d. I don't know why that helps me remember it, but for some reason it does. So if that's helpful to you, then you can also use that little mnemonic device. But yeah, it's low, right? The bottom, d high, so derivative of the top. So low d high minus high d low. So low d high minus high d low over low squared. Okay. Well, so let's do this then. So we're going to do g times f prime, that's going to be 3x squared, plus 2 times 2 is 4, 2 minus 1 is 1, so 4x, and then 0. So this is g f prime. Then we're going to do minus f, that's x cubed plus 2x squared minus 1, times g prime. Derivative of x plus 5 is just 1, so there's g prime, over g squared, so that would be x plus 5 squared. Right? That's just g squared. Okay, the rest is just a matter of simplification. So the rest is algebra, right? Let's distribute this and distribute. Well, there's nothing really to distribute, but we'll distribute this and then we'll combine our like terms. So we're going to have 3x cubed plus 4x squared plus 15x squared plus 20x minus x cubed minus 2x squared plus 1, right, when we distribute the negative sign. And then that's all over x plus 5 squared. I'm not going to bother to FOIL out the denominator. Best case scenario, once we finish combining our like terms in the numerator, we might be able to factor it. And if we can factor it, then we might be able to cancel with something down in the denominator, in which case we want the denominator to be factored. We don't really want the denominator, so expanding it isn't really going to help us, is what I'm trying to say. Let's see if that even happens. It would be fairly unlikely to happen, but we might get lucky, who knows. So 3x cubed minus x cubed is 2x cubed. And then we've got 4x squared, 15x squared, and a negative 2x squared, so I think that's going to bring us to 17x squared. Then we have the 20x, the 1, and can we factor this thing? maybe. You'd have to, I mean, it's a 4-term polynomial, so you could try factoring by grouping. I can tell by looking at it that's not going to work. If it does factor, I guess you would have to do something like the rational roots theorem, rational zeros theorem, do factors of 1 divided by factors of 2, and test them using synthetic division, right, etc., etc. Something tells me we're not going to get an x plus 5 out of that, though. Because how can you get an x plus 5 when your last term is a 1? So, anyway, I think that's as far as we're going to go with it. Okay, let's do another one. So we'll do y equals 2x to the 7th minus x squared times x minus 1 over x plus 1. Ooh, this is a good one. Because actually what you have is a product rule and then a quotient rule inside of the product rule, right? So I'm going to think of this as f. I'm going to think of this as g. And what I have here is f times g, so I need to do a product rule. So dy dx is going to be f times g prime plus g times f prime. So let's see what we've got. F times g prime. So g prime is going to take a little bit of scratch work, I think. So if g of x is x minus 1 over x plus 1, I could think of this as h1 and h2. I need to do, so for g prime, I'm going to do low d high minus high d low over low squared. Okay, so let's do that. So it's going to be low x plus 1 times d high, so derivative of x minus 1, that's just 1, minus high, that's x minus 1, d low, so derivative of x plus 1 is just 1, over low squared, that's x plus 1 squared. Okay, so I've done f and g prime. Now I need to do g, so I'm going to say plus g times f prime. F prime is a little easier. 7 times 2 is 14, so this is 14 x to the 6th minus 2x. So this is g and f prime. So that's all the calculus. Now the rest is algebra, right? Let's see if we can clean this up. 2x to the 7th minus x squared. I'm going to have an x plus 1 times an x minus, or sorry, an x plus 1 minus an x minus 1. So this is really x plus 1 minus x minus 1. That's x minus x is 0. 1 minus negative 1 is 1 plus 1, that's 2. So I think this whole thing just simplifies down to 2 times x plus 1 squared. Okay. To simplify that much further, I think we would probably get like common denominators and stuff. I don't know if I'm going to take it that far, but we can definitely multiply these things, right? So I'm going to do it like this. I'm going to say this is 2 times 2x to the 7th minus x squared over x plus 1 squared plus x minus 1 times 14x to the 6th minus 2x over x plus 1. I'm not exactly sure how much further we would take this. I suppose I could do that and then combine them into a single expression. And if I'm going to do that, then I might want to multiply out the numerators so that I can go ahead and combine like terms. So let's do it. 4x to the 7th minus 2x squared plus, I'm going to go ahead and well, actually x minus 1 times x plus 1. If I had just put this thing over here, that would have gotten me an x squared minus 1, right? So this is x squared minus 1 times 14x to the 6th minus 2x. So that's just from combining those two. Okay, now let's see. 4x to the 7th minus 2x squared. Here we'll have a 14x to the 8th, and then a negative 2x cubed, and then a negative 14x to the 6th, and then a positive 2x divided by x plus 1 squared. Do I have any like terms? I don't have any like terms. All that work for no like terms. Can you believe it? Well, we can at least write it in descending order. We've got 14x to the 8th, and then a 4x to the 7th, and then a negative 14x to the 6th, and then a negative 2x cubed, a negative 2x squared, and a positive 2x, all over x plus 1 squared. I'm really curious if that thing factors. I mean, it's an even number of terms. All these last terms have a 2x in common. We'd be left with x squared. If we took out a negative 2x, we'd be left with x squared plus x minus 1. But that doesn't match over here. Unless this 4 was supposed to be a 14. I don't think so, though. Because, yeah, that's where we get the 4. Well, that's too bad. It doesn't factor by grouping. Again, you could take out an x at least. But I'm trying to see if it'll cancel with like the x plus 1 down there, and I don't think it does. Possible. To see if it does, I guess you could do synthetic division with just negative 1, just to see if x plus 1 is a factor of the numerator. And then if it is, then you can cancel an x plus 1. But that's as far as I'm going to take it. Okay. I want to give you one more example. So let's find the exact locations of the horizontal tangent lines to the graph of f of x equals x squared minus 1 over x to the 4th plus 1. Okay. So remember, so if you have a horizontal line, its slope is 0, right? And the derivative is the same thing as the slope of the tangent line. So really, what this boils down to is we're going to find the derivative of the function. That's going to give us the slope of the tangent line in general. But if we want to know where that slope is 0, then we're going to set that equal to 0 and then solve for x. So first we've got to find the derivative though. So it's going to be low d high, moving a little quicker, minus high d low over low squared. What? I don't know why I said squared and then wrote cubed, but there you go. Okay? Now we want to know where this thing is equal to 0. Okay? So we want to set this thing equal to 0 and then solve for x. Well, if I clear denominators by multiplying by the denominator there, well, I'm just going to get the numerator, right? I'm going to get 2x to the 5th plus 2x minus 4x to the 5th. Maybe I should read this. 4x to the 5th minus 4x cubed. So that's 2x to the 5th minus 4x to the 5th, so negative 2x to the 5th. And then I have a negative makes a positive 4x cubed. And then I've got a positive 2x. And suddenly that doesn't look so bad, right? We've just got to try to factor that. Definitely I can take out a 2x. In fact, I'll take out a negative 2x just to make that leading coefficient positive. And I have x to the 4th minus 2x squared minus 1. Okay. Can we factor this? To get a negative 1, you'd have to have a negative 1 and a positive 1. That's not going to give you negative 2, so it doesn't factor. So we have to use quadratic formula. Notice that this trinomial is quadratic in form, right? You could do a substitution if you like. You can call x squared, you could say let x squared equal u. And then this would just be u squared minus 2u minus 1. And then you can solve for u, and then back substitute to solve for x. I'm just going to use the quadratic formula with it as is. I know that, so I know that one solution, you can say negative 2x equals 0, or right, x to the 4th minus 2x squared minus 1 equals 0. If negative 2x equals 0, then that just means x equals 0. So there's one of the exact locations where you have a horizontal tangent line. But the others are going to come from here. So I'm going to say, okay, if x to the 4th minus 2x squared minus 1 equals 0, then x squared equals negative b plus or minus square root of b squared minus 4 times a times c, so really that, over 2 times a. Okay, so that's 2 plus or minus 4 plus 4 is 8. Square root of 8 is the same thing as 2 root 2. That's not bad at all. So 1 plus or minus root 2. But that's x squared, right? We need to solve for x. So x itself is going to be, we're going to take square root of both sides. We're going to get x is plus or minus the square root of 1 plus or minus square root of 2. So be careful. You've got 4 solutions here, right? You don't have to list them out, but just so that you're aware, right? It's like one of the solutions is the square root of 1 plus root 2. Another solution is square root of 1 minus root 2. Another solution is negative square root of 1 plus root 2. And then the fourth one is negative square root 1 minus root 2. So those are all the exact locations, right? So there are 5 places in total where you have horizontal tangent lines. That's really interesting. I'm interested in looking at this function in Desmos just to see. And I guess we should be careful too, because if any of these solutions make our original denominator 0, then actually you don't have a horizontal tangent line there. What you have is a place where the function is undefined. I don't know if that happens though. Goodness, if you square this and then square it again, you're not going to get negative 1. So yeah, I don't think that happens. Just out of curiosity, how long have we been going? Oh, for 38 minutes? Yeah, let's take a look at this in Desmos. So I'm going to look at the original function, f of x equals x squared minus 1 over x to the 4th plus 1. Okay. And So we definitely have a horizontal line at 0. Okay, that's making sense. Right, like the slope of the tangent to the curve at that point is the horizontal line. We've got another one that looks like maybe that point right there and there. So there are two of them, but we came up with 4 solutions. What are these? This must be so square root of 2 is like 1.4. So 1 plus the square root of 2 is like 2.4. That's not this value. This is like 1.5-ish. That's interesting. I may have made a mistake somewhere. Because 1 minus root 2, oh, it's the square root. Duh. Okay, sorry. Let me see about how much that is. Right, so remember, these are our solutions down here. So square root of 1 plus square root of 2. Oh, I see the issue. Here's the issue. So these ones, this one right here and this one right here are not real numbers, because square root of 2 is bigger than 1. It's like 1.4. 1 minus 1.4 would be like negative 0.4. So the square root of that's not real. That's why we're only getting two solutions. But yeah, the square root of 1 plus square root of 2 is about 1.55. And yeah, that's what we're getting here. So we're getting the positive one and the negative one. So everything makes sense. We actually only have those 3 solutions because these other 2 are not real numbers. Okay. So so that's that one. I'm glad we looked at this in Desmos so that we knew that, oh yeah, those can't work because they're not real. Anyway, that's all I have to say about that.